Hi everyone. Welcome to part 1 of a lecture covering some more specific effects on metals due to temperature. In this lecture, I will use aspects of previous lectures to describe the net effects of temperature on materials once they've been solidified, and implications for in-service or post-processing heat treatments. Let's start first by revisiting the potential energy versus interatomic spacing curve, which I presented in earlier lectures. I showed that differences in the shape of the net potential energy curve can describe why thermal expansion alters for different materials based on bonding strength. This is important to appreciate, but within the context of the present lecture, the more important aspect to appreciate is demonstrated with a singular curve. The strict definition of temperature is that it gives a measure of the average kinetic energy of particles in a system. For a given type of bond, particles oscillate about E0 position for any given temperature T0. The point being highlighted here is that as temperature increases, atoms move further apart. While we're on the topic of interatomic separation, in early lectures I demonstrated how the interatomic force curve for different materials could be used to demonstrate how the modulus can vary between materials. Now let's use the same framework to look at a single material as temperature increases. If atoms are now further apart with an increase in temperature, then the mean interatomic spacing will also increase. When at absolute zero, i.e. when the atoms aren't moving at all, then the modulus for a given material will be at its peak. This is shown here where the atomic separation curve is at an equilibrium point. The net force is zero. The immediate slope or differential of the force versus separation curve at this point is the modulus. If the separation is increased, then the differential changes. We start to see the slope decreasing as the interatomic separation increases. That means that as we start approaching the melting point of the material, the rate at which the modulus changes increases, approaching a point where the modulus is effectively zero, something you'd expect when you start arriving at a liquid state. The elastic property is not the only thing that changes, though. Let's now look at plastic behavior. Here is a plot of some various stress-strain curves at different temperatures under slow loading for two materials, commercially pure iron in red and an aluminium alloy in blue. At extremely cold temperatures, iron demonstrates no ductility. Then, as it's tested with increasing temperatures, both the yield point as well as the overall ductility increase as well, as characterized by the strain to failure. While cryogenic behavior of the aluminium alloy was not available, it can be seen here there's roughly the same type of behavior noted. The yield point and the plastic behavior are very different when changing the temperature. It should be noted that aluminium and iron have different moduli, 70 versus 200 gigapascals respectively. And this is not readily apparent here, but the emphasis being depicted is the change in plastic behavior. Note that at the highest temperature for aluminium, the rate of work hardening is nearly linear, implying that it can be deformed indefinitely with relatively low stresses. Beyond the fact that there are two dramatically different underlying crystal structures whose baseline ductilities are different, the main reason for this type of behavior is that the resistance to dislocation movement diminishes dramatically as temperature increases, regardless of the metal and underlying crystal type. By the end of this lecture, you'll be able to appreciate why. Before we get into plastic effects, we need to spend a bit of time looking at transport mechanisms within a crystal structure. Let's look back at solidification under non-equilibrium conditions, as shown here by the copper-nickel system. It's been described how the system, if cooled, quickly creates a single phase upon cooling to ambient conditions, albeit with a non-uniform distribution of copper in the nickel, or as I've shown it here, with non-uniform nickel in the copper. This is because cooling quickly denies the ability to allow diffusive transport of nickel to make the alpha have a uniform allocation of nickel everywhere. If we were to take a segregated alpha structure as shown on the right and hold it at sufficient temperature for a long enough time under the equilibrium solidus, it will end up with a normalized alpha which has a consistent distribution of nickel everywhere. This is achieved by giving the transport mechanism of diffusion everything that it requires to make this happen. Let's examine this process a bit further. If I had a block of pure copper and a block of pure nickel, and pressed them against another, I would have the arrangement demonstrated on the left. We can draw the concentration of both copper and nickel in this situation on the lower left, a stepwise function. Holding these two blocks together and bringing the temperature up to approaching the lowest solidus temperature for the copper-nickel system, then diffusion turns on and there is a driving force for nickel atoms to enter the copper and vice versa, as shown on the right. After some period of time, the further one moves from the interface between the two materials, then there returns to be a pure concentration of each. Immediate to the interface, then one would have an even distribution of copper and nickel. This process is called interdiffusion, whereby the process of diffusion and mixing occurs freely, to the point where a homogeneous mixture is obtained. This is what would happen if this situation were to be left long enough at a high enough temperature, where the function of concentration versus position would end up being a straight line for both copper and nickel. Let's look at the mechanisms that make this happen. In a previous lecture, I told you that vacancies can occur within crystals, positions which should hold an atom on a statistic basis, but do not. These occur everywhere within metallic crystals. In fact, the main motorway for atoms moving about within a solid crystal. One can consider this two ways. Either the vacancy moves or the atom moves, but in opposite directions. As an atom moves to occupy a vacancy, then this vacancy will also move. On this basis, the diffusional transport of a host species, i.e. the self-diffusion of nominal lattice atoms, or a substitutional atom, as in the case of our copper-nickel system, can occur. Either a host or substitutional atom moves into a vacancy, which then moves the vacancy in the opposite direction. If an interstitial atom is considered, however, there is no movement of a vacancy because interstitial atoms do not need a vacancy to move. Instead, the movement of an interstitial atom employs space which is already existent within the lattice to move. This is the relationship between diffusive transport of atoms and vacancies within a crystal lattice. While the mechanism is apparent, what is the main driving force behind diffusion? Fick's first law of diffusive transport gives us a framework to explain what's happening. It's all driven by concentration at any given point. Where there is a high concentration gradient, then there is a driving force for diffusive transport. What I'm showing here is a one-dimensional representation of Fick's first law. At a location where the concentration of species A versus B is very high, then the diffusive flux will be correspondingly high as represented by J. The rate at which this happens is dependent on a coefficient D, which is characteristic of the system A and B, as well as the rate at which the concentration of A and B changes with position. For metallic crystals, the main route for substitutional diffusion is driven by temperature and the number of vacancies. But the number of vacancies is also a function of temperature. As the mean interatomic spacing increases, so too will the number of vacancies. Let's see how. The rate at which vacancies increases is a function of not just the temperature, but also the number of potential sites which could host a vacancy. There is an activation energy for forming new vacancies, which at low temperatures is minimal, but as temperature increases, then there are an increasing number of vacancies which are created. The end result is that the number of vacancies increases exponentially with temperature. This is a big implication for the rate at which diffusive transport of host or substitutional atoms can occur as a function of temperature. It's not surprising then that the diffusion coefficient captured in Fick's first law follows roughly the same formulation. The diffusion coefficient increases exponentially with temperature, with the D0 and Q being characteristic of the system at hand. Furthermore, if an increase in temperature increases the diffusion coefficient for substitutional or host atoms, then it will increase significantly for interstitial diffusion. This is because interstitial diffusion does not need a reciprocating vacancy to move, the vacancy already exists as free space between atoms. And if the mean spacing between atoms increases with temperature, then the barriers to movement are all the more diminished. For metallic crystals, the big picture here is that regardless of whether substitutional or interstitial transport needs to take place, there is a dramatically lower barrier to this form of transport as temperature increases. The increased numbers of vacancies diminish with the overall activation energy for diffusion, such that the diffusion coefficient increases exponentially with temperature, in turn increasing the diffusive flux exponentially with temperature, even though Fick's first law is a linear relationship. So, in this part of the lecture, it's been demonstrated that the modulus of elasticity diminishes as the melting point of materials is encroached from absolute zero on the basis of interatomic separation. As the temperature increases in metallic crystal structures, the mean separation between atoms increases. This affects the rate at which phase changes can occur and how much of a departure from equilibrium conditions are apparent. There is a dramatic increase in diffusion rates as temperature is increased, and this has been explained on the basis of vacancy generation and concentration gradients according to Fick's first law. I've also presented empirical evidence that both the overall strength of materials decreases and plastic behavior evolves with increases in temperature. However, on this latter point, I have not explained how. This will be described in the second part of this lecture. Until next time.